and then you can simulate QCD as accurate as you want. Indeed, you need a fantastic computer to make these calculations sufficiently fast. But my belief is the answer to the question is yes. It is not obviously known, certainly not mathematically proven. In fact, there's $1 million waiting for someone to prove the existence of a mass gap in QCD with mathematical accuracy. Physically, we all believe there's a mass gap, and physically we believe we understand QCD so well that we have our ways to compute anything we like. But we also use a lot of hand waving. And so I think your question should be split into two questions. One is, can we do it with mathematical precision? That's to say, can we do a calculation where we are under control of all the possible errors that we make, and we can compute with complete certainty within which margins the mass of a certain particle lies? That's a very hard question. I don't think that will happen very soon. But the other question is, will our technology, our techniques be improved sufficiently well to do accurate calculations for QCD? How accurate will they be? I mean, this is a question that has been around for years. I think actually the two questions, the one with pure mathematical logic and the other with where you ask for fast, convergent computation techniques, I think the two questions are linked.
No, but
if you understand the mathematics very well, you'll also be able to do the computations much better.
Yeah, but say you could do them perfectly. Is that the end?
If you can do what?
If you could do the calculations perfectly, would that then be the end?
I'm sure that people who will be able to do such calculations will discover lots of things that they'll be fighting about. And so I don't think that will be the end. It will be an important milestone for QCD. I mean, the situation you describe has more or less been reached for QED, right? Because for QED, we can do perturbation expansion to any order we want. And the reason why we stop is that we hit about thousands or millions of diagrams, and that goes beyond today's computers, but not the computers of the future, we could hope. So, but nevertheless, QED is not a perfect theory. It has its lambda ghost, and we know that when you try to do 137 loops in QED, then for certain you will hit a divergence that you cannot overcome anymore. So then the theory is in trouble again. So mathematicians will say QED doesn't exist because after 137 loops you can't do a computation anymore. And if physicist says yes, but we stop at 3 or 4 or 5 loops, and then we think we're very clever. We don't ever reach 137 loops, so we're not going to ask that question at all. Such differences also exist between QCD from a formal point of view and QCD from a practical, pragmatic point of view. So pragmatically, we will very possibly, in a not so distant future, be able to do very accurate QCD calculations. Formally, mathematicians will always complain that you haven't really proven that the theory you talk about exists in the mathematical sense, because we don't really know whether the computations converge. It's not such an academic question as you might think. For instance, we think of doing the perturbation theory of QCD and doing the Borel resummation. But then you hit upon all the instanton singularities and renormal singularities, and you've discovered they are a problem. Not only practically, because it's very hard to do any calculation there, but also from a more fundamental point of view, that the divergences in the infrared, they have a crosstalk to divergences in the ultraviolet. So if you want to have the theory very accurately defined in the ultraviolet, you first will solve the infrared part. But we thought that induction would go in the other direction. So there is a circular problem in QCD of which it's not obvious that we will be able to solve it. And I am confident that yes, in principle, it can be solved. It probably will be solved by someone a lot smarter than humanity today. But it's not going to be an easy problem.
John?
Hi. Dr.
Where are you sitting?
I'm speaking here.
Ah.
In your slides, you wrote down the solutions for one instanton configuration. I'm wondering, is there any systematic way that you can write down the solutions for many instanton configuration so far?
Well,
what's the difficulty of that?
It is a subject of a quite considerable mathematical literature. It's not so easy. I did happen to tumble into a solution of arbitrary many instantons, but not the most general one. A very special solution. One can write down a solution with any number of instantons, and that is an exact solution. However, it's not the most general solution. We know that there are much more solutions, and in fact, mathematicians know a lot about those solutions. I'm not totally sure whether they have written them out, all of them explicitly. I would not be surprised if someone by now has succeeded in doing that. I haven't followed all those details. But the problem becomes much severe if you take n instanton and one anti-instanton there as well. Then, in principle, that's unstable, so that doesn't need to be any solution, but maybe you can have metastable solutions or accidental solutions of that sort, and then the question becomes again very, very hard. But as I said, the mathematics literature is full of this, and not only instantons, but then you go to higher dimensions, or magnetic monopoles is the other question. Are there exact solutions for magnetic monopoles, particularly in the Borromolny case, where you have first order equations for magnetic monopoles? Then again, you can write down the n monopole configuration. There are formally these things can be solved, but to what extent explicitly, it always turns out to be very difficult to write down just from scratch the explicit solutions, although mathematicians have made quite considerable literature on these issues.
The mathematicians have reduced the problem of instantons, finding instantons, to an algebraic problem.
Yes.
Which is hellishly difficult to solve, but anyway, it's progress.
Yeah.
And thanks to that, the calorons that you mentioned this morning were found due to that mathematical apparatus.
Right. Okay. Thank you.
Sastre?
Hi.
Yes.
My question is, self-dual configuration are always solution, but are there solutions that they are not self-dual?
I very briefly hinted upon that in principle you could think of an instanton, anti-instanton. The instanton is self-dual, the anti-instanton is anti-self-dual. You put them together, that's not a solution. Yeah. But maybe accidental solutions exist. I'm not sure of this. Intuitively, I would say possibly they don't exist, because that configuration is unstable. The instanton, anti-instanton will attract and annihilate each other. And so, possibility is that they are simply unstable. So the only stable, or only exact solution, I should say, will be purely self-dual or purely anti-self-dual. And the discussion among mathematicians is indeed one of algebra rather than of the differential equations, which are under control. So the question is whether there are exact solutions which are not of that type, and then you land in a much more complicated mathematical problem. Of course, we can, in four space, not in Euclidean space, but in Minkowski space-time, there are lots of solutions in principle of plane waves and which are disturbing each other. So then you know that in principle, iteratively, by doing all sorts of approximation techniques, you can approximate a solution. But that's not really, usually that's not really what we want. If finding one specific solution in a whole forest of different possible solutions is physically not very meaningful, so few people are busy with that.
Is there any other questions? Okay.
I would like to report on the experimental needs for instantons to be there. And the point is that when the story started, namely the fact that the mixing, pseudoscalar mixing and vector mixing were different from zero and not equal. This story was deduced from bubble chamber physics. And then we needed to go to non-bubble chamber devices And the first instrument, which is now old, but the first time that we went from bubble chamber to non-bubble chamber instruments had as a program, among other things, like the lepton and the study of the time-like form factor of the proton, was just the one which, if Professor thooft allows me, I would like to show the diagram, because this very interesting theoretical discussion is based on the fact that no matter what those problems need to be solved, but instantons are needed indeed. The only explanation for theta pseudoscalar different from theta vector, as shown in the first esso caspita di sempre Zambito. Yes.
Yes, that picture.
You see, this is the pseudoscalar and vector mixings, not using the mass formulae, because mass formula was trivial, in other words, repeating story. You see, the eta and eta prime are very near to SU3 flavor axis, while the vector phi and omega, they are as if SU3 was not there. So it was a big problem. And the only theoretical support I had in CERN was due to John Bell, and the only theoretical fellow who started to think about this is Gerardo thooft. Without instantons, this is just not there.
But of course, as you know, theoreticians want instantons for totally different reasons. But this, of course, is an example of convergence. So the prediction that instantons have to exist in QCD came from totally different arguments. It is a field configuration that may spontaneously arise in any QCD environment. So we get this configuration, and it will have an effect on quarks. And when you see the way they act with chiral symmetry, of course, then the eta problem jumped to my mind. I knew about the problem. The problem had been taught to me by Veldman as a serious problem, which was one reason why he was very critical against any attempt to write down such QCD-like models for quarks. He said it can't be right because of this strange mixing of the scalar mesons.
Yeah.
And of course, as a theoretician, you then ignore all these warnings, and you do it anyway. So you say, well, this problem will be sorted out some way or other, and much to our surprise, you found that the problem had a very natural answer within this theory, and that answer was the instantons.
We cannot forget that the eta prime, when you are talking about the origin, was taken to be tensor meson. The people who showed that la smetti di giocare con questi cosi, the proof that eta prime was a pseudoscalar is coming from us with this instrument. The 2 gamma decay of eta prime was discovered by us. The eta prime was not in this graph. It was considered a tensor according to bubble chamber physics. And the non-bubble chamber physics proved that the eta prime goes into gamma and therefore is quantum number 0 minus. Now,
so those were interesting days in physics where experimentalists had their way of figuring out what the true state of